Hey there, 2200. If you're watching this video, we're going to do Faraday's Law of Induction together. Well, actually, we're going to do part B together. Traditionally, this lab has been broken up into two parts, an A and a B, and it takes 2 weeks to do. What we're going to focus on is the part B today. I think your instructors are going to have you do both parts in 1 week, and the reason being is that if you had to go into the lab yourself, it'd be more time consuming. You'd have to figure out how to hook this equipment up, take the data and whatnot. But since this is being provided to you with the video, it's gonna be a lot quicker. So maybe I'll do part A in another video, but right now we're doing part B. And I'm gonna say a few words just to motivate why, or the purpose of this particular lab. So I have a coil of wire. Let's say that it's connected together, and I put a magnet near these coils of wire. There's a field, and that field is going through its center. So there's a magnetic flux through the center of this wire. Now, if I have it stationary, the question is, would there be a current going through this loop? Well, the answer is no. Faraday's law of induction states that it has to be a changing magnetic flux through the center of the loop for there to be an induced current. So if I move this back and forth, the field or magnetic flux is constantly changing, so that would cause a current through the loops. Another situation would be if I had both of these objects stationary and I simply just varied the strength of the field of this magnet. Well, obviously I can't do that with a bar magnet, but if this was, say, an electromagnet where I could increase the strength by turning up the voltage, then decreasing the strength by decreasing the voltage. So I did that off and on, off and on, off and on. Over time, what I would be doing is, of course, varying the field so the magnetic flux that's going through these loops of wire is constantly changing again, so we get a current through these loops. And the last situation would be the orientation of these loops. If these loops are situated this way, you can see that there is no magnetic flux going through the center of these loops. If I have it like this, some maximum amount of magnetic flux is going through the loop. So if I constantly changed it, the magnetic flux that is going through the loop is constantly changing, and in effect, there'd be a current through the loops. So for part B, what we're gonna do is have stationary coils, and we are going to put a current through these loops. In fact, we're gonna have an alternating current so that the field that this creates is constantly changing. Now, at some distance over here along the axis of the center of the loop, we're gonna have what we call a pickup coil. And that pickup coil is going to have not only a magnetic flux going through it, it's gonna have a changing magnetic flux going through it. So as that magnetic flux through the loop is changing, there's gonna be an induced current in these coils. And we're going to measure what that current is and validate two laws, Faraday's law of induction and the Biot-Servat law. So what we are interested in are two laws, the Biot-Servat law and Faraday's law of induction. So what kind of experiment can we do which will validate those two laws? Here we'll have a Helmholtz coil set up. We'll run a current through them, and according to the Biot-Servat law, a magnetic field will be produced. We are going to calculate the magnetic field that those coils produce along this region in space here. It's along an axis that passes through the center of these loops. Now, that magnetic field can strictly be determined based on the law. The law not only tells us that a field will be created, but it tells us, it gives us this mathematical form so that we can indeed calculate it. These coils could be of any arbitrary shape. That would be hell, though, to calculate the field produced by an arbitrarily shaped wire. So we have this very good symmetric setup so that that field can indeed be determined. Likewise, we have this search coil here, and the magnetic field in this region that is varying over time will induce an EMF in these coils. And what we'll do is use Faraday's law of induction to calculate the field at this particular region based on the measurements we take from the current passing through those coils. In other words, we've just used two separate laws to determine the magnetic field at particular points along this region, and we'll compare the two together. So if those laws are in fact valid, and of course we do the experiment right, in other words, set up the circuit and our measurements are done correctly, those two values of the magnetic field should be equal to each other, of course within experimental error. Okay, what you see here is page 56 of your lab manual, and depicted is a diagram of the circuit we're going to make. So let's quickly, just briefly talk about each of the elements. What we have is a 6.3 transformer. Now, what that thing is going to do is kick down the 120 volts coming out of the wall down to 6.3. Actually, I don't know if that one there is specifically a 6.3 volt transformer, but it's somewhere in the vicinity. What we also have is a variac, which is this here. You can consider that basically the same thing as this here, with the exception that you can alter how much output voltage this thing allows. In other words, you can go from 0 to 100%. Incoming is 120 volts. The output could be varied anywhere from 0 to 120 volts. Logical question, however, now that I think about it, is why even use this guy, right? Why even kick down the 120 volts to 6.3 if we have that there? And the reason being, well, it's all about safety. You could inadvertently have that pretty high up on its scale, and you'll be working with a current that's like close to 120 volts, and you can get hurt. Not only that, but the current from a voltage source that high is going to be incredibly high. So the current in these wires will generate a lot of heat, insulation could melt, equipment fails. So this is like a safety device. So we're going to plug this into our variac so that we can vary the incoming 120 volts anywhere from 0 to 120 volts. This is plugged into that, so this further knocks that voltage down to anywhere from 0 to 6.3 volts. We are going to connect this ammeter in series with our circuit so that it reads the current at any given time. We'll also have this resistor hooked up in series so that we can monitor how much current is actually going through our circuit. We do that by hooking up in parallel the oscilloscope, so that at any given instant in time, I know what the voltage across this 1 ohm resistor is, and in effect, I could calculate the current through my circuit at any time. Then our circuit will include 1 or 2 of these coils of wire, depending on which part of the experiment we're doing. And from here, I will connect back to my transformer so that I have a complete circuit. The thing I didn't mention is the search coil. The search coil is this device here. It may look a little complicated, but all it is just coils of wire along that plastic cylinder there. And what its function is to pick up the magnetic flux that's going through it. And that changing magnetic flux that's going through that those loops of wire will induce an EMF, and we'll measure that with our oscilloscope and be able to determine the current that's going through that loop. All right, guys, let me say a few words about our collection of data. What your lab manual wants is this Z distance. Now, when we do the part where there's only one coil, the Z value is the distance from the center of this coil to the center of the pickup coil. Then, when we do the experiment where we have the Helmholtz coil set up, both of these set up together, the Z value then changes to the center of these two coils to where our surge coil is placed. So Z Helmholtz is this, Z for the single is this. Now, to record where the center of that surge coil is, I suppose we could just eyeball it. But I don't know, I think maybe I have OCD or something. I can't do that. A fine line between OCD and good lab practices, I guess. I have to be a little bit more rigorous. What I did was measured the thickness of the coils, which is 0.315 centimeters, divided that by 2, and I measured the distance between this edge and the edge of this base plate, because what we're going to end up doing is measuring the position of this surge coil by where this plastic edge of the base of the surge coil is up against the ruler, instead of just eyeballing where this falls on the ruler that's located right here. So half of 0.315 plus this here, which is 0.96, equals 1.118 centimeters. You know what, let's just call it 1.1 centimeters. That's too many significant figures anyway for our purposes. So the offset is 1.1 centimeters. So this is how I went about collecting the data. My single coil, well, let's talk about this position first. The center of these two coils is positioned at 20.0 centimeters. And I did that by adjusting this ruler. So the Y value of the Helmholtz coil position, the origin for the Helmholtz coils is 20.0 centimeters. This position right here happens to fall at, give me a second here, 25.4. So this is at 25.4 centimeters. So when I'm taking data, what I'm doing is I'm looking at the edge of this plastic base and recording that. And that is what I'm calling Y surge coil base. So to determine what Z is, when we're using just a single coil, the Z value is the position of the surge coil base minus the position of the single coil, which is this distance here, minus this distance, minus the offset on the surge coil, which is 1.1 centimeters. So that's a precise location to the distance between the center of the surge coil and the center of that single coil. Then likewise, for the Helmholtz coil, to find this Z, I simply measure where this base is up against the ruler. That's my Y surge coil base. I subtract the Y Helmholtz coil, which is this 20 centimeters, never changes, minus that offset, which is, we're leaving that at 1.1 centimeters. Now, this is all straightforward, and it gives us a precise way of determining exactly what these Z values are, where we don't have to eyeball it. In all fairness, if we did eyeball it, we would still obtain good data, but I think this is good practice. into doing things the more correct way. You know, if you're when you start doing research with results that need to be more accurate, you would want to take these things into account. So if it's a bit confusing, I don't know, maybe I'll report at the end of the video a collection of the data we obtained in terms of just Z, so you don't have to worry about this. But again, this is pretty straightforward.
Whew.
Okay, so we have our circuit set up and we're ready to take data. Almost ready. Remember, we are going to set up a particular current in these loops, and that is determined by the position we have in our variac. Right now, the current that is going through there is displayed on channel 2. Peak to peak is 1.64 volts. What I'm going to do is make it, let's say, 2.5. So I'm just fine tuning it right now. So although the peak to peak will eventually be 2.5, we know that the voltage across this circuit is half of that, right? Half of the V peak to peak value. So half of 2.5 will be 1.25. And I should just leave well enough alone. You see how it's going back and forth between 2.48 and 2.52. Okay, I'm not going to touch it. I'm going to leave it alone. I'll be here forever. So our channel 2, which is the blue curve, is measuring the voltage across this resistor here. Now, since that resistor is 1 ohm and Ohm's law states that V is equal to IR, R is equal to 1 ohm. In other words, V is simply equal to I, numerically anyway. Volts is in voltage is in volts, and current is in amps, of course, but numerically they're going to be the same value. So the volts is 1/2 of 2.5, 1.25. So I know that I have 1.25 amps going through this coil there. By the way, we have an analog ammeter here, and if I was to take that reading, which gives us the root mean square voltage, and multiply it by the square root of 2, that would give me the voltage from this base up to the tip. In other words, if I divided the peak to peak voltage of this blue curve by 2 and compared that to the analog reading times square root of 2, they'd be equal. And they are. So our circuit is set up correctly. And for now on, we're just going to rely on the oscilloscope to give us voltages and in effect the current going through this resistor. And for the duration of this part of the lab, we're not going to mess with that anymore. We know the current and we're going to keep it there. So in fact, you might want to make note of that. The max amplitude of the current going through that loop is 1.25 amps. I just got rid of the channel 2 display because we don't need that anymore. The yellow curve is channel 1, and channel 1 isn't hooked up to this circuit. It's hooked up to this search coil. Now notice this search coil isn't hooked up to any battery or voltage source. It's just hooked up to the oscilloscope. And you'll see that there is indeed an EMF induced in that coil, and that's not coming from an outside source. It's simply coming from the magnetic field produced by these Helmholtz coils. So if I move this search coil closer to these coils, it'll be moving it towards a stronger field, and the EMF should increase, which it does. And if I move it in the opposite direction, the field is weaker and the magnetic flux that's going through that coil gets smaller and the EMF goes to almost zero. Now, for this experiment, we want to measure the EMF induced in that coil at different positions along this axis through the center of the loops. But there's a bit of a problem. That signal is pretty noisy. So if we were to just rely on these measurements, by the way, I do have time in mind. This video is going to be somewhat lengthy, but I'm cutting it down to half of what, as long as it was turning out to be. I preset these displays to the measurements of interest. For instance, channel 1, the voltage peak to peak, channel 1, frequency, channel 1, search coil. And like I was saying, notice there's a bunch of noise in that curve. So if I was to look at this peak to peak voltage, it really isn't 12.4 millivolts. That isn't a good representation of what that peak to peak is. In fact, let's prove it. I'm going to use these cursors here to put at the peaks. And it's showing me a delta V of 10.6 millivolts, yet my voltage from peak to peak is registering somewhere around 13. What it's doing is it's picking up those little spikes. It's picking up that noise. So we are going to try and clean that up a bit. So that's a much sharper curve. So you can see now it's measuring 8.4 millivolts peak to peak. Let me readjust these cursors. So according to those cursors, my delta V is 8.6 millivolts, and the V peak to peak reading is 8.8, 8.6. It's fluctuating a bit because it is picking up a little bit of noise, but you could see now how we can just rely on this reading and not have to mess with the cursors every time we move this along the scale. And I mean, I wouldn't mind doing that, but we'd be here for hours because I'm shooting for like 20 different data points. So we're going to start off with just current in this first loop here. And the origin of this, the center of this loop, is located at 25.4 centimeters. So we're going to start off with the base of this search coil at 25.4 centimeters. And I'm doing that because that puts the actual coil dead center in the middle of that coil, in the middle of this large coil. Whoa, what the hell was I thinking? I gave you the first data point. Your Y value was 25.4. To put the surge coil in the center of this coil here, that was totally wrong. It should be 25.4 plus 1.1 centimeters, which is the surge coil's offset. First data point is therefore 26.5. I mean, it still gives you a voltage of 44.4 millivolts, but no, I don't know what I was thinking. Anyway, back to the video. This large coil. So your Y surge coil base is at 26.5, and let's see what EMF is induced in that coil. 44.40 millivolts. So now let's get another position. I'm going to move it to the base is now at 27.0 centimeters. And my V peak to peak in that surge coil is 44.4 millivolts. Same as before. Let me move this along a centimeter. So now it is at 28 centimeters. And the EMF from peak to peak is 43 point, it's fluctuating a bit, 43.6. Move this over to 29 centimeters. And I'm at 40 point, okay, I'm going midway, 41.0. I place this at 30 centimeters. And we're at 38.0. 31 centimeters. 34.8. Right now, I could tell it's dropping. In fact, I already know what this graph looks like. And in this particular region that we are in with the surge coil, it's going to fall off rather quickly. So I'm going to go move it along at a smaller increment. 31.5 centimeters. 33.2 millivolts peak to peak. Move this over to 32.0 centimeters. And we are at 31.2. Don't worry, I am not going to just increase the distance by half a centimeter all the way to this point. We'll pick up the pace in a second. 32.5 centimeters. And the peak to peak voltage is, we'll call it 30. Okay, now we'll put it at 33 centimeters, and then we'll start advancing by 1. But now we're at 33.0 centimeters, and the peak-to-peak voltage is 28.0. 34 centimeters, 34.0. And we are at 24.8. Okay, for the sake of time, I was tempted to go a half a centimeter, but we'll go a full centimeter. So now we're at 35.0 centimeters. And our voltage peak to peak is 22.0. And of course, so far all of these voltages are measured in millivolts. So now we're at 36.0. And our peak to peak, 19.20. Or 19.2. We're going to keep this at 3 significant figures. So now we're at 37. And it is, I'll go with 16.4. Okay, now we're going to, from 37, skip all the way to 40. So at 40.0 centimeters, our V peak to peak is 11.6. 11.6 milliamps. I'm sorry, millivolts. So now let me jump to 43. 43.0 is 8.4. Yeah, see, if it was up to me, I would probably go in smaller increments, but that's just me. 1, 2, another 3 centimeters puts us at 46.0 centimeters. And our V peak to peak is 6.0 millivolts. Or I should say 6.00. So we're keeping it to 3 significant figures. Now let me advance it another 3. So now we're at 49.0 centimeters. And it is at 4.4. Actually, let me change the scale here. .4.08 it is. Let me make sure that, yes, we're still averaging, getting rid of that noise. So now let's move it over another 3 centimeters. And we're at 52.0 centimeters. And our V peak to peak is 3.12. Okay, let's go ahead and move it over 5. So we are at 57.0 centimeters. Our V peak to peak is 2.48. Excuse me. Move it over another 5. That puts us at 62 centimeters, 62.0 centimeters. Our V peak to peak, and I wish I could increase the scale, but that's the limit. We are at 1.84 millivolts. And just because our surge coil has a little bit more room to travel, I'm going to end it on 64. 64.0 centimeters. We are at 1.92. Okay, 1.92. Wait a minute. Let me... $1.76. That wasn't that bad, right? Part B of this experiment that deals with this equipment here involves what we just did here with one coil, then doing it all over again with Helmholtz coils, which is 2 coils set up together. So we'll do that momentarily. Okay, guys, time for part 2. By the way, I want to apologize for this setup. I have this tiny tripod and, you know, I'm in my son's room and you can't really see everything that's going on this table here, but I'm doing the best I can with what I have. Any future videos will be better quality, hopefully, maybe not. Anyway, we are going to use both of these coils now. So what I'm going to do is disconnect this plug, put it in that one. Now current is running through 2 coils at the same time, and we're going to do the same experiment. As a side note, the benefit of having 2 is that for regions close to the center, the field is uniform. There's more uniformity that can be obtained otherwise if you were to just use one. And in your lab manual, it explains why. In fact, they break down the equation of the Helmholtz coils into a Taylor series expansion, about 0, of course, and they're able to show how the X, there's no X dependency. If this radius is equal to the distance between the 2 coils, then there's not even an X squared dependency. It's an X fourth dependency. So when you're really close to the origin, that X to the 4th power term has little effect on the field. But with that said, we are going to go and place this surge coil. Let's see if I don't make the same mistake as last time. We want to place this surge coil dead center. In other words, get the center of that surge coil right over 20 centimeters, which means I should put this at 21.1 centimeters, because after all, 1.1 centimeters is the offset between this surge coil's base and the actual surge coil. So right now, the surge coil is at the origin. And let me move this oscilloscope in front of the camera here. Let me get a better scale. There we go. And Good thing I remembered. Your instructors may ask you to compare the field produced by the single coil with the field produced by the two coils at specific points. He may or may not. If he does, there is an equation in your lab manual that relates the two, which becomes meaningless if the current in each setup is different. So what I want to do is set up the same current in these double coils. Now, so far I haven't touched that variac there. I haven't altered the potential, but just by virtue of hooking both of these coils up, it's going to change because there's more resistance. I just added resistance to our circuit. So I'm displaying channel 2 again, the blue curve, and what I want to do is measure the peak-to-peak voltage, which, if you recall, in our first coil was 2.5. So as I increased the current, I'm increasing the voltage, and in doing so, I am increasing the current in our main circuit. The surge coil current is picking up as expected, but we don't care about that right now. I just want to fine tune the current in our main circuit, which again is indicated by the blue channel 2 curve. And again, I'm going to stop right there. It's 2.48. We'll call it close enough, right? In fact, it's fluctuating between 2.48 and 2.52. So it's the same as the other setup. Now, get rid of it. We don't need it anymore. Let me scale the voltage reading in our pickup coil. And as I said before, the base of our surge coil is at 21.1. Now it's at 21.1. It was at 21 before. And what is the EMF produced in that surge coil? V peak to peak is 61.20 millivolts. And just want to make sure it's averaging. Yes, it is. And again, that was to reduce the noise. So now I'm going to move it to 21.5. So 21.5, I'm getting a V peak to peak of 61.2. Now I'm going to move it to 22 centimeters, 22.0 centimeters. V peak to peak is 61.2. Instead of going half a centimeter, I'll move it along the whole centimeter. So our base is now at 23.0 centimeters. And my V peak to peak is 61.2. I'm going to move this along a whole centimeter. So I'm at 24. And my V peak to peak is 61.2. Now, if you recall from our last data set, we only had to advance that surge coil by like 1.5 centimeters before the voltage, the induced voltage, started to drop off. So far, we've moved it like 3 centimeters, and it's still the same. And that goes back to that Taylor series expansion I was mentioning on how a set of Helmholtz coils, 2 coils in other words, produce a more constant field in the center here. So let me go a whole nother centimeter. So now I'm at 25 and I'm at 60.4. So now it's starting to drop a bit. Let me just go 0.5 centimeter, 25.5, 60.4. So it's still hanging in there. Now I'm at 26.0 centimeters. V peak to peak is 59.6. 26.5 centimeters. I'm at 58.0 millivolts. Now I'm at 27 centimeters. And I'm at 57.2 millivolts. I'm at 27.5 centimeters, and that gives me 56.0 millivolts. .28 centimeters, or 28.0 centimeters, 54.0 millivolts. Okay, for the sake of time, let's go up a full centimeter. 29.0. I'm at 50.4. .30 centimeters. By the way, nothing would please me more than to analyze this data for you, or with you, I should say. But hey, so you're going to gain experience, right? 46.8. .31 centimeters. Okay, after this I'll start advancing it at a larger distance. 42.0. Okay, let's go 2 centimeters. So now I'm at 33.0, and my induced EMF is 33.2 millivolts. I'll advance it 2 centimeters again. At 35.0 centimeters, we are at 26.0 millivolts. Another 2 centimeters. Then after this, I'll start increasing the distance. So 37.0 centimeters is 20.4. Okay, I lied. It's falling off rather quickly, so I don't want to be too hasty. You'll get a better curve if you have more data points in the sections of the curve that vary more rapidly. So that's 39.0. 15.6. So now we're at 41.0 centimeters, and I'm at 12.4 millivolts. Go another 2 centimeters, which puts me at 43.0 centimeters, and I'm at 10.0 millivolts. Okay, let's increase it by 3. I'm at 46.0, and that gives me, we'll go with 7.60 millivolts. I'll increase it by 3. That puts us at 49.0 centimeters. And we're at 5.6. Call it 5.4. I advanced it 3 centimeters, so that puts us at 52.0 centimeters. We're at 4.40. It's fluctuating a bit. Whatever, 4.40. Move this along 3. That's 55.0 centimeters. And my voltage it's fluctuating. Okay, I'm going to make it an even 4.00. Move it along another 3 centimeters. We're almost done. 48.0. All right, 3.8. And I wish I could increase the scale, but I can't. It's a lot of noise. Technically, that's closer to 3.12 when we took a 3.8 reading. But I mean, I suppose if we wanted to be more accurate with the experiment, as we're moving along and we noticed those spikes, we may want to just abandon that reading and take readings from this cursor. But we're already almost towards the end. So we're going to pretend like we didn't see that. Okay, 61.0 centimeters gives us 3.5. That is way off, so I am in fact going to use the cursors. So the cursors give me a delta V of 2.48. And we will consider this a done deal. Okay, we are almost done. All I need to do is give you a few measurements that I took off camera and you'll be able to analyze the data. First of all, to calculate the magnetic field of your main coil, you'll use this expression here. You'll need A, which is the radius of that main coil. Radius of the main coil is 10.5 centimeters. Also, you need N, the number of turns in that coil. That is 135. The current that was running through that coil was the same for both experiments. Here's Ohm's law, V is equal to IR. And again, that resistor was conveniently chosen to be 1 ohm so that the current will equal your V peak to peak divided by 2, which turned out to be 1.25. So current is 1.25 amps. Here's the magnetic field calculated by the induced EMF in your search coil. By the way, I apologize. Sometimes I call the search coil a pickup coil, but hopefully that didn't cause any confusion. You will need the number of turns in that search coil. Number of turns is 100. The frequency of the induced EMF in that search coil was 60 hertz. I didn't mention that during the experiment. I was keeping an eye on it on the oscilloscope, and it was indeed 60 hertz for every measurement, as it should be, because after all, the voltage supplied to our main circuit was coming directly out of our wall outlet, and our homes are, of course, wired to be 60 hertz. A is the effective area of the search coil. That can be found with this expression here. You'll need both R and S, where R is the inner radius of that search coil, 1.27 centimeters, and S is the outer radius, which is 1.35 centimeters. So to get your induced EMF, remember, it's not your V peak to peak voltage that you recorded, it is half that. So divide your experimental or our readings that we took from the oscilloscope by 2, and that'll give you your electromotive force. Now, real quick, I'll just recap on how we got our Z positions. So for the single coil, what we're going to do is get our Y search coil base measurement and subtract from it the position that the single coil was in, and this 1.1 centimeters, which is the offset between the search coil and its base. So our Y single coil was positioned at 25.4 centimeters. These two numbers total to 26.5 centimeters. So for our single coil, our Z values are simply our recorded values minus this. So this number is constant. Just subtract 26.5 centimeters from that data we took, and that'll give you your Z's. And for the second part of the experiment where we did the double coil, the center of that double coil was located at 20.0 centimeters. So the number we want to subtract is 21.1 centimeters. So again, these here are all of our measurements. And once we subtract this value from that measurement, we get the actual Z, or displacement. of our search coil from the center of the Helmholtz coils. I already graphed this data. It looks really good. You'll find that I believe we did, in fact, validate both of those laws. And hopefully you don't have too much difficulty. You will want to reproduce the f of x and g of x curves. I know that there's some provided for you in the lab manual, but you don't want to use those. Mainly because their A is slightly different from ours. Ours is better. It's 10.5. I think they used 10 centimeters. But not only that, they ran a different current through their circuit. Their current was, I believe, if I'm not mistaken, 1 amp, where ours is 1.25. So have fun with that analysis. You will find that it looks great. And until next time.